All right, so the law of conservation of momentum. Momentum's a vector property, as I keep on saying. The total amount of a system, total momentum of a system before an interaction is the same as the total momentum of that system after an interaction. I'll tell you what I mean by that. Some people go for walks in the summer, and I can remember lots of summers going for walks with my dad along the creeks, around the Niagara area and around Burlington and around the escarpment. And what you notice as you walk enough is that there's a lot of seeds along the pathway, particularly in these little creek valleys and in the undergrowth. And the seeds that are my favorite are the ones that burst when you touch them. The ones that they like pop. And then when they pop, they shoot seeds all over the place. It's actually a seed pod full of seeds. And if you can find them during the spring or the beginning of the summer, it's really fun because you can pick them up and you can throw them at your friends and they go pop, and it's a blast. It doesn't make a lot of noise like that, but it's cool. Anyway, small things amuse small minds, and I had a good time as a kid. So I've got this little seed pod here, and it actually has segments to it. And when you disturb it, the segments burst apart, as we see here. Now the thing is, before, if the thing isn't moving, what's its momentum? Zero, absolutely. So I'd say that the total momentum, I'll call it PT for total, is 0. 0 kilogram meters per second if you like, but 0. Now once this thing gets disturbed, it blows apart. And so a part of it flies off in this direction. We'll say that this is part 1. Part 2 maybe flies off in this direction. And part 3 maybe flies off in this direction. It explodes. You've seen things, pop before. All the pieces go in different directions. But make a prediction. If the momentum before is 0, what should the momentum after be for the system? 0. Oh, I messed up. Anyway, so prediction should be that P primed total should be 0. And if we were going to look at this, we'd have to have a nice high rate of frame collection type of camera, something with a high frame rate. But what we would have to see is what the displacement over time was for each of these in different directions. And it would be a two-dimensional problem. Really, this is a 2D conservation of momentum problem. But what we would do is calculate, using the mass of this object, and this object, and their velocities, a momentum sum vector diagram. And so momentum 1 might go off like this. We might call it P1. Actually, we'd probably call it P1 primed, because the prime indicates that it's after the interaction occurs, so it's the momentum of that portion after the explosion occurs. P3 primed might look like this. I tried to draw it about right. And P2 primed goes off like this. Oh shoot, I didn't quite do my vector diagram justice. My angles are a little bit off. The idea though is that these vectors added tip to tail, each of them added tip to tail, should come back to where you started from. And if it ends up coming back to where you started from, it would confirm that the total momentum after the explosion is 0. Now I could have chosen something that was less benign than a seed blowing up. What's something that I might have chosen? Like a little bit more violent maybe.
Bomb.
Yeah, a bomb or a grenade or something like that. I don't want to choose examples like that, although people often pick those up. You definitely could do that. And what you would find is, if I was able to, with a fast frame collection camera, take a look at this ballistic thing blowing up, the momentum of each individual shrapnel piece actually should add up to being a total momentum of 0. Of course, in that case, you'd be dealing with a 3-dimensional scenario, because things blow upwards, downwards, and side to side. So it's a little bit more complicated. But in the end, the total momentum should end up being 0.
Great.
Yeah, it's kind of neat. I don't want to talk about explosions for too long. I want to talk about collisions, though, because explosions and collisions could both be used to get at this, and I like collisions a little bit better. So I want to try this example. A train collision. A huge train with a mass of 10.0 kilograms rolls along at 10.0 meters per second to the right. hits a little train. I know, it's not a very big train. I would just being silly. You're right. It's a little train. 10.0 kilogram train going at 10 meters per second hits a little train that is stationary. Well, let's give it a mass too. That is 5 kilograms and stationary. Okay? So big and little are relative terms. So I've got my big train here. I'm going to call it mass A. And mass A...
It looks like one of those cool commercials where the flag.
Mass A, 10 kilos. Moving along with VA equals 10.0 meters per second. I'm going to say that to the right is positive and to the left is negative. And it's going to collide with a little train, little in mass, but equal in volume. A little train we're going to call mass B, 5.00 kilograms, and it's just stationary. So we could say that VB is equal to 0 meters per second. Now I could calculate the momentum before for these two trains. I could say that PA is equal to MAVA, or, well, it's 10 times 10. I'm not gonna sub in all my values here. I'm just going to write the final answer. 100 kilogram meters per second. And PB, peanut butter, is equal to, what should I call it? MAVA. MB, VB. And really VB is 0, so I'm just going to say that it's 0. Because anything times 0 is 0. Now that's the before scenario. Now, a lot of people like to break up interactions between multiple masses for momentum conservation and energy conservation into before and after situations. So on the left is going to be before and on the right is going to be after. But here's the question. After the collision, the little train had a velocity of 8.00 meters per second to the right. And what I'd like to do is find the big train's final velocity. Oh, I was going to do it to the right of the orange dotted line. I guess I'm going to have to do it below. And I'm going to need some people's help with the calculation. So have your calculators ready. Alright, some things that people like to figure out off the bat before we even start. We've already got PA and PB. I'd like to find PA primed, prime indicating that it happens afterwards, which is going to be MA VA primed. And I'd like to find PB primed, MB VB primed. Okay? So the speeds are, or sorry, the velocities are primed and the momentums are primed. You don't have to prime the mass because the mass stays the same. Let's not be crazy here. Yes, sir. Yeah. So PB primed, 5 kilograms times positive 4 meters per second. Oh, sorry, positive 8 meters per second. My fault. Thank you. Ends up giving us 40.0 kilogram meters per second. And we don't know PA primed yet. We'd like to come up with some way to do it. We said before that P total should be equal to P total primed, and that's still going to be true. And I know this is a nice round number. Some people have already done it in their heads. We're just going to go through the process of showing the communication for the occasion when it's going to be more tricky, okay? So we get P total before is actually equal to PA plus PB. P total after is PA primed plus PB primed. And PA, well, let's get the thing by itself that we want by itself. It's PA prime. So we'll say PA plus PB minus PB primed is equal to PA primed. And so we could write PA primed is equal to MA VA plus MB VB plus, plus negative, I suppose, MB VB primed. And we've already done some of these calculations, so I'm not going to sub in the numbers again. We said before that PA was equal to 100 kilogram meters per second. We said before that PB was equal to 0, and we said that MB VB primed was equal to 40 kilogram meters per second, but it's negative now, so 40 kilogram meters per second. And as Michael said before, I know you did it as your head math, and that's okay because the numbers are nice and round. You end up getting 60 kilogram meters per second. That's pretty reasonable, but that's not the question. What was the question again? Yeah, find the velocity. We can do that though, because this is mass A, and we already know mass A. We know that mass A is equal to 10.0 kilograms. Okay, so VA primed is equal to PA primed divided by mass A. No problem. And I've run out of space, so this is bad form. But I'm going to sub in my values horizontally. 60 kilogram meters per second divided by 10 kilograms. Kilograms cancel out, and we end up getting 6.00 meters per second. And it's a positive value, so that indicates that it's going to the right. I think that works out pretty well. So we can use conservation of momentum to figure out what the final velocity of one of the items is if we know the velocity of the other item after the collision. There are other details that we can definitely work out, and we will as we go along. I want to try something else though. Now that we've talked about conservation of momentum, and this is just in one dimension, we'll get into 2 dimensions before you know it. I want to see what happens to the energy. So we've said momentum is conserved, and I'll let you in on something. Momentum is always going to be conserved. But I want to see what happens with the energy. Because people always say, well, momentum's conserved, energy's conserved, everybody's happy. Actually, can I give it to you in a couple minutes?
Yeah, sure.
Okay. I want to lay out an energy argument here. What about energy conservation? And I want to think about the 2 trains that we just discussed. So the 2 trains have masses. I'll do it in dark. Mass A is equal to 10 kilograms. Mass B equal to 5 kilograms. I'm dropping off some decimal places because I want to talk this out fairly quickly. VA was equal to 10 meters per second. VB was equal to 0 meters per second. VA primed was equal to 8 meters per second. Is that right? No. 6 meters per second, sorry. Yeah. 6 meters per second, my fault. And VB primed was equal to, what was it again? 8 meters per second this time? Okay. 8 meters per second. And so I want to check to see if energy is conserved. Momentum was conserved. I want to see if energy was. So we'd say energy total, that would be energy total before, is it equal to energy total after? Well, let's find out. I don't want to put that equal sign there. I want to put a dotted line in between them and figure them out separately. Check to see if they're equal. E total would be 1/2 MA VA squared plus 1/2 MB VB squared, and E total after would be equal to 1/2 MA VA primed. I'm going to put that in brackets so it doesn't look like VA to the power of 12. VA primed squared plus 1/2 MB VB primed squared. And if you plug in your values, well, you tell me, what do you get for the before scenario? Well, we could do this in our heads, actually. VA is 10. 10 times 10 is 100. MA is 10. 100 times 10 is 1,000. Times 2 is 500. So I can say that this is 500 joules. And this one's just going to be 0 because VB is equal to 0. On this side of the equal sign, VA primed, that's 6, 6 squared is 36, times a mass of 10 is 360, times 0.5, 180, right? Good so far? Anybody want to weigh in? Does that make sense? Okay. VB primed, 8 squared is going to be 64. 64 times 5. Somebody help me out here. 320? 320 times a half is 160. Good so far? So 180 plus 160. We get 340 joules. Uh-oh. Those are not the same thing. That means that that equal sign is not true. We showed that momentum was conserved. We said that PT was equal to PT prime. You can go back and do the calculations, make sure we didn't make any mistakes. But what we can't say is that E total is equal to E total primed. We just can't say that. There's a missing 160 joules. So we could say that E total is equal to E total primed plus energy lost. And the amount of energy that's been lost has been 160 joules. And I'm going to let that simmer for a little while. I want you to just let that sink in. And we'll come back to it. And we'll talk about the fact that energy doesn't have to be conserved even though momentum is conserved. I just wanted to put it out there. And we'll come back to it later.